Right, so the next example, we set up the augmented matrix very quickly. That's going to be a 0, 2 minus 1. Okay, it's going to be a 2 minus 1, 2, 7. It's going to be a minus 1, 3, 1, and minus 2. Okay. Right, so clearly there are no 0 rows to worry about, so we will basically go on to the next step. So we locate the leftmost column that has at least one non-zero entry. Okay, and so it's going to be this column here. Then we look at the non-zero entry in that column, any non-zero entry, and we want to make sure that it is placed as high as possible. So I can either start with minus 1 or 2. I'm going to start with minus 1. Right, so we're going to switch the third row with the first row. So basically we're going to take the third row and we're going to take the first row, switch it around, and then we're going to take the first row and replace it with the third row, like so. Then the highest leading entry in the foremost left column, we're going to use to create zeros under that leading entry. So we want to make this a 0. Okay. So how we're going to do that is we're going to change the second row by adding twice the first row. Okay, so multiplying the first row with 2, I get minus 2, 6, 2, and minus 4. And now I'm going to add it to the second row. So the first entry is going to be 2 minus 2. And that is going to be replaced by a 0. Then the second entry is going to be 6 plus minus 1, which is 5. So I'm going to replace minus 1 with 5. Then the third entry is going to be 2 plus 2, which is going to be 4. So I'm going to replace that with 4. And then the last entry is 7 plus minus 4, which is going to be 3. Okay, now we perform the next step. So we do an imaginary cancellation of the first row that contains the first leading entry. And we look at the column that's furthest to the left that has at least one non-zero entry. That is below the cancelled row. Now you've got two non-zero entries there to choose from. You can either choose to start with 2 or with 5. I'm going to start with 2, and I want to place 2 as high as possible. So I'm going to do this by switching the second row with the third row. Okay, so I'm going to interchange the two rows. Alright, and remember we place the 2 as high as possible, but it needs to be below the cancelled line. Okay, so interchanging the second and the third row, we replace the second row with the third row and the third row with the second row. And so there we've placed the 2 as high as possible under the first row. And what we're going to do now is we want to create zeros beneath the 2. So we want to make all the non-zero entries below 2 in the second column 0. So there are a variety of ways we can do that. What I'm going to do is I'm going to change the third row by adding to it minus 5 over 2 times the second row. So multiplying the second row with minus 5 over 2, first entry becomes minus 5. The second entry becomes 5 over 2. And the last entry becomes 10. Okay, and now we're going to add it to the third row. So the first entry, non-zero entry in the third row, becomes minus 5 plus 5, which is 0. So we can replace that with 0. Then the next entry becomes 5 over 2 plus 4, okay, which is 13 over 2. And then the last entry becomes 13. Okay, so next up we're going to go to the last row and create a leading 1. And we can do this by taking the third row and multiplying the third row with 2 over 13. So doing that, we can replace the first non-zero entry in the third row. We can replace that with 1. Okay, and then we take 13 and we multiply it with 2 over 13. And that gives me, I can replace 13 then with 2. Right, so now we are in a situation where we can actually solve this linear system easily. We've solved for the variable z essentially, and we can use back substitution to solve for x and y. So writing down the linear system that corresponds to this reduced matrix becomes, the first equation becomes minus x plus 3y plus z equals minus 2. The second equation becomes 2y minus z equals minus 4. And the last equation becomes z equals 2. So now having solved z, we don't have to do any further manipulation of the matrix, although we can, it's not necessary. We can now solve this linear system. So taking 3 and substituting it into 2, we get from 2 that 2y minus 2 is equal to minus 4, and so we can solve for y. Okay. So y becomes minus 1. So now we've solved z and y, and we can do a further back substitution by plugging the values z equals 2 and y equals minus 1 into the first equation. So then we get minus x plus 3y. We solved y as minus 1. And plus z, and we solved z as 2. And so from there we can then just solve x. So therefore x becomes 1. Right, so we solved z as 2, y as minus 1, and x as 1. And note that it was only necessary for us to solve one of the variables and use back substitution. We didn't have to do any further manipulation to the actual matrix. Okay, so next up we've got Gauss-Jordan elimination. So Gauss-Jordan elimination is just a variation on Gaussian elimination. So you just taking one extra step. So how this works is you write down the augmented matrix of the system of linear equations. Then what you do is you perform Gaussian elimination to reduce the augmented matrix to row echelon form, which is what we just illustrated. Although in the last example we didn't fully reduce the matrix to row echelon form because it wasn't necessary. We used back substitution. But in this case you write it into row echelon form, and then what you do is you locate the rightmost leading one, and you reduce the entries above it to zeros by adding a multiple of this row to the ones above it. So with Gaussian elimination, when you did row echelon form, you took your leading entry and we created zeros beneath it. The difference now is you don't only create zeros beneath it, you create zeros above it as well. And then you basically continue this process with each leading one, moving from the bottom of the matrix to the top. So essentially you're just further reducing it, and then what you do at the end is you solve the resulting system easily by inspection. So you don't use back substitution in this case, you just directly read off the solved values. Right, let's look at a quick example. So here, write down your augmented matrix. We take 3, 1, 2, and 2, minus 2, 1, minus 1, 1. Alright, so now what we do is no zero rows to consider here, so we don't have to start off with switching initially. So now you locate the leftmost column that has at least one non-zero entry. It is this column here. The non-zero entry, I can pick any one. I can pick minus 2, 3, or 1. And whichever one I pick, I need to make sure that it's as high as possible. I'm going to pick 1 because this is going to be the easiest. I don't have to do any switches, interchanging of rows. So I'm going to pick 1 as my leading entry, and I'm going to use this 1 to create zeros there below it. Okay, so we know already how to do it. I'm going to change the second row by basically multiplying the first row with 3 and adding it to the second row. Okay, so doing this, we get the first entry, we get minus 3, we get 3, we get minus 3, and we get 0. And now we add it to the second row. First entry becomes a 0. The second entry becomes a 4. The third entry becomes a minus 1. And the last entry becomes 2. Okay. Now I need to create another 0 by changing the third row. So we change the third row by multiplying 2 with the first row and adding it to the third row. So doing that, we get 2 minus 2, 2 and 0, and add that to the third row. The first entry becomes a 0. Okay, the second entry becomes minus 1. Okay, the third entry becomes 1, and the last entry stays 1. Okay. Right. So now we've created a leading entry in the first row, which is in this case it is this. It's that value 1. Okay, now we created a leading entry in the first row, which is this 1. So now we're going to discard the first row, not physically cancel it. You cancel it, you do an imaginary cancellation. And now what you do is you locate the leftmost column that has at least one non-zero entry. Now the leftmost column that has at least one non-zero entry is this column here. And now what we want to do is we want to place a non-zero entry in this column as high as possible so that it still stays below the black line. Okay, now I can either do minus 1 or 4. What I'm going to do is I want to place I'm going to start with minus 1. And I'm going to place it as high as possible. I can also do 4 if I wanted to. It doesn't really matter. So I'm going to interchange the second row with the third row. Okay, so that can easily be done. You take the second row and you move the third row into the position of the second row. Okay. And then you replace the third row with the second row. Okay. Right, now I need to create zeros below it. This is going to be my next leading entry, and I want to create zeros below it. So I want to make that a 0. I'm first writing it in row echelon form. So I can do this by changing the third row. And I'm going to do this by multiplying 4 with the second row and adding it. Okay, so basically, So you're going to multiply that with 4. That's going to be minus 4. That's going to be 4, and that's going to be 4. Okay, so now add that to the last row, and we're going to get the first entry is going to be a 0. Then the second entry, non-zero entry, is going to be, and the last entry is going to be 6. Okay. Right, then the last row we're going to change quickly by multiplying through with a third. So the first entry becomes a 1. We replace 3 with 1. And the next entry we can replace with 2. So I've made a leading 1 there. And now we can use this leading 1. Remember, now we need to create zeros above it. We need to create zeros below it. We don't have any to consider, and we need to create zeros above it. So I'm going to change the second row by adding minus the third row to it. So in this case, you're going to multiply the third row with minus 1, so that's minus 1 and minus 2. And then you're going to add it to the second row. So basically, minus 1 plus 1 is going to be 0, and minus 2 plus 1 is going to be minus 1. Okay, so that takes care of that part there, and we need to create another 0 there. Alright, so we're going to change the first row by adding negative the third row to it. Okay, so getting the negative as multiplying that with minus 1, we get that, minus 1 and minus 2, and then we add it to the first row. So basically that is going to be, that's going to be 0. And that the next one is going to be minus 2. Okay, so note that because we made these entries 0, they don't have any bearing on this part, that side of the first row. Okay. All right, next we create a leading 1 in the second row, which we know how to do that. We're going to multiply the second row with minus 1. So the first non-zero entry in the second row is going to become positive 1. And then the last non-zero entry in the second row is also going to become plus 1. Okay, now again, what does Gaussian-Jordan elimination tell us to do? We've created zeros below here. We've created zeros above. And now this leading 1, we need to create zeros above it as well. This leading 1 is covered because we've already got zeros below it. We don't have to worry about zeros above it because there aren't any. Right, so we're going to change the first row by basically adding the second row to it. Okay. Okay, so multiplying the second row with 1, we get 1, and I get 1 there. And then I'm going to add it to the first row. So 1 plus minus 1, that first entry I'm going to replace with a 0. And that last entry I'm going to replace with minus 1. Okay, so now we are in a position where we can solve this system by inspection. So that corresponds to the system x minus 1, y equals 1, and z equals 2. Right, so Gaussian-Jordan elimination just takes a Gaussian elimination a little bit further, and you completely solve the whole system using matrix operation and not just back substitution. Okay, let's do one quick final example here. So write down the augmented, just another Gaussian-Jordan elimination example. So that's 1, 2, and minus 1, 5, and minus 1, minus 1, 1, minus 2. 2, 1, minus 2, 1. Okay. Right, so after this, I'm going to assume that you guys already know this procedure now. It's not difficult, very, very elementary and straightforward. You just have to practice it a little bit. We won't be spending any more time on this. So this will be one of the last examples that I'll do on this. All right, so now what we're going to do again is we don't have 0 rows to contend with. We are going to select the leftmost column that has at least one non-zero entry. This is that column, and I'm going to pick any number, either 2, minus 1, or 1, and I'm going to place that right at the top, and I'm going to use that as my leading entry. Right, I'm going to choose 2. So again, you're going to take the third row and interchange it with the first row. Okay. Right, so we're going to switch the 2 around. Okay. Right, so that's my 2 is my leading entry there, and I'm going to create zeros below it. I'm going to do this by adding to the second row half the first row. So multiplying the first row with a half, we get 1 there, we get a half there, we get minus 1 there, and we get a half there. Okay, so let's add it to the second row. That first entry, we get that to be 0. The second entry, we get that is going to be replaced by minus a half, and the next entry is going to be replaced by 0, and the next entry is going to be replaced by minus 2 plus a half. It can be replaced with minus 3 over 2. Next up, we want to create another 0, and I'm going to do that by changing the third row and multiplying the first row with minus a half. Okay, so doing that, we are going to get the multiplying through by minus a half the first row. That's going to be minus 1. That's going to be minus a half. That's going to be plus 1, and that is going to be minus a half. Okay, add that to the last row. That entry there is going to become 0. The next entry is going to be 2 minus a half, which is, it's going to be 3 over 2. Then 1 plus minus 1, which is going to be 0. And then the last entry is going to be 5 minus a half, which is 9 over 2. Right, so I've created zeros below the leading entry in the first row. So now the first row I've taken care of. Now I'll move on to the second row. You go and locate the leftmost column that has at least one non-zero entry. The leftmost column that has that property is this column here. And we look at the, we select a non-zero entry and we place it as high as possible. Now I can either select this one or this one and place it as high as possible. I'm going to select this as my non-zero entry that I'm going to work with. So we're going to basically interchange the second and the third row. I don't have to do that. I can keep this my leading variable, but I'm not going to do that. I'm going to use the one below it. Again, it can cause extra work, but this is just to illustrate the problem. So again, what you're going to do is you're going to take the second row and you're going to replace it with the third row, like that. And you're going to do that. Okay. Right, so I'm going to create zeros below 3/2, so I can change the third row by adding a third of the second row to it. Okay, so let's do that. And what you're going to do is you are going to multiply the second row with a third. So that is going to be a half there. And the next one is going to be 3/2. Okay, so let's add that to the last row. So a half plus negative a half is going to be 0. And 3/2 plus negative 3/2 is also going to be 0. Okay, so there we've got it. And remember, I just forgot to mention, this value you have here, remember that was the value in that column that we placed as high as possible, that non-zero value. That's my leading entry. You place it as high as possible, provided that it is under the black line. Okay. So you don't fiddle with the first row. You've already fiddled with it. You've created your leading entry there. So everything below it, that is of interest. Okay, so the last row goes to a 0 row. Okay, and now what we can do is create a leading one in the second row. Okay, so basically you're going to take the second row and you're going to multiply with 2/3. Okay, so the first entry is going to be 3/2 multiplied by 2/3, and that's going to become a 1. And 9/2 times 2/3 is going to be, that's going to be 3. Okay, right, so now what we do with Gaussian-Jordan elimination, we have to go one step further. We have to create leading ones, and we have to basically not only create zeros beneath them, we have to create zeros above them as well. So firstly, let's just create a leading one in the first row. So you're gonna take the first row and you're going to multiply with a half. Okay, so that entry 2 is going to become, right, the second entry is going to become a half. The third entry is going to become -1. The last entry is going to become a half. Okay. So now locate your leading ones. That's the leading one there. Okay, there are zeros above it, below it. There are no entries above it, so I don't have to worry about anything above it. So go to your next leading one. That's my next leading one. I've got zeros below it. That's cool. So I need to create zeros above it. So I want to eliminate that term there. So how you do this again is you change the first row by multiplying the second row with negative a half and adding it to it. Okay, so again, so multiplying that becomes negative a half, and that becomes negative 3/2. So add that to the first row. That entry is going to become a 0, and the next entry is going to be a half plus -3/2. So that is going to be -1. Okay, so you're going to replace that with -1. Okay, so now you can now solve this system basically primarily by inspection. You write down the system corresponding to that, so that becomes x plus 0y minus z is equal to -1. That's the first equation. The second equation is 0x plus y plus 0z is equal to 3. Okay, and so from there you can immediately solve for y. You can solve for y as 3. Right, so continuing there, we get then that x, so basically from 1, you get basically that x minus z is equal to minus 1. Okay, and then we see that we have to parameterize. Alright, so let's just go back to the previous page, right? So remember what we said, the leading ones correspond to my leading variables. So which are the leading ones here? That's a leading one, and that's a leading one. Okay, so the leading ones correspond to the variable x and y respectively. Okay, so meaning that the remaining variables are free variables. And with a free variable, we always assign a parameter to a free variable, and then we solve the remaining variables in terms of that parameter, or parameters, depending on how many equations you have in your system. So going back here, so we need to, z in this case is my free variable. Okay, so we can let z then be a parameter, t, which is a real number. And so we can solve for x. X is going to be t minus 1, which is the same solution we got with Gaussian elimination. So my solution set then becomes, it's all points where x is t minus 1, y is 3, and z is t. Okay, and t is a parameter, it's any real number. You can choose t as any real number that you wish, and you get a solution point. Okay, so next up we've got homogeneous linear systems. We've already talked about homogeneous linear systems in section 1.1, so just to recap, a system of linear equations is called homogeneous if the constant term in each equation is 0. So it's basically you have a linear system here with n unknowns, and it's got m equations, and basically each equation is of the form where you have a polynomial on the left and you've got a 0 on the right hand side. Now if you look at the augmented matrix of this homogeneous linear system, the last column will comprise of zeros only. Now, a homogeneous linear system is always consistent because it's got at least one solution, and this solution is the trivial solution. It's a solution where each x is equal to 0. So a solution is called a trivial solution if it assigns 0 to every variable. So in this case, if we make x1, x2 up until xn, if we make them all 0, that surely is a solution. So homogeneous linear system is always consistent, and we refer to other solutions to be non-trivial. Now, a homogeneous system of linear equations, as I said, always has the trivial solution, so it's always consistent. In the case of homogeneous linear systems, there are only two possibilities for a solution set. Is either it has only the trivial solution, or the system has got infinitely many solutions in addition to the trivial solution. Now you can actually prove this, and we'll do this later on. If you take a homogeneous linear system, and this linear system has at least one non-trivial solution. So at least one non-trivial solution, meaning that at least one of your x's is not 0. Then basically you can go and use this non-trivial solution to go and construct a set of infinitely many solutions. So therefore you only get two possibilities. Either it has got infinitely many solutions, or it has exactly one trivial solution, because having a non-trivial solution will immediately imply that it has infinitely many solutions. Right, quickly look at this homogeneous linear system. If we were to solve this again, if you write down the augmented matrix. Okay, and again we can basically change the second row by adding the first row to it. Okay, so the first row multiplied by 1 is 1, that's 2, that's minus 1, and adding that to the second row we get we get 0, we get 1, we get 0. Okay. Okay, so in this case here we can easily see that that corresponds to the system y equals 0 and x plus 2y minus z is equal to 0. Okay, and so from there we can make y 0 in the first equation. So again, from 1 we get x plus 2 times 0 minus z is equal to 0, and so that implies that x is equal to z. Now remember, the variables corresponding to the leading ones are my leading variables, and whatever remains is a free variable. So I have to, again, I have to parameterize my free variable, which in this case is going to be the variable z. So from there we can just basically complete by letting z be t, where t is a parameter, and so the solution space then becomes, it's all points where x is t, y is 0, and z is t. Alright, so again, that is a solution to a homogeneous linear system. Okay, now we've got our first theorem, theorem 1.2.1. This theorem for homogeneous linear system, it's called the free variable theorem for homogeneous systems. Now what it says is, if a homogeneous linear system has n unknowns, and if the reduced row echelon form of its augmented matrix has r non-zero rows, then the system has n minus r free variables. Right, now you can easily you can see this if we look at the augmented matrix. There's your augmented matrix, okay, and we've written this in row echelon form. Okay, now I've made leading ones. Okay, so there are all my non-zero rows. Okay. Okay, and there is my last column. These columns will always be zeros. Okay, so now eventually we're going to get to my zero only rows. Okay, and so I'm going to say basically that these are my non-zero rows, and there are how many of those? We said there are such non-zero rows, and the number of 0 rows will then basically be it will be whatever remains. Okay, so that will be my number of 0 rows. Now, why do we have n minus r free variables? Now remember, if we go and count the number of leading variables, if we go and count that, we're going to have r leading variables. Okay, so counting that number of leading ones there is going to add up to r. Now, how many variables does this system have? This system has n variables. Okay, it's got n variables. It's got n unknowns. We said this. It's got n unknowns there. So therefore, in total, we've got n unknowns, and we've got leading variables. How many leading variables? We've got leading variables adds up to r. So that is going to be the number, whatever variables remain once I've cancelled all the leading variables. That's going to be my number of free variables. Okay, free variables. Okay, so one can easily see that. Then theorem 2, a homogeneous linear system with more unknowns than equations has infinitely many solutions. A homogeneous linear system with more unknowns than equations has infinitely many solutions. All right, so let's quickly look at a proof of theorem 2. What we're going to do is just let the homogeneous linear system, let it have n unknowns and m equations, where n is strictly bigger than m. So it's got more unknowns than equations. All right, now if we look at the structure of this matrix, if we go and write it down, this augmented matrix of this system, it will have m rows and n plus 1 columns. Because remember, the n plus 1 comes from the extra row column of zeros that you get right at the end. So you're going to have n columns, firstly, that correspond to your variables, and then you've got the last column that corresponds to the all the zeros. Right, so if we then just draw the structure of this matrix, the yellows indicate the number of columns there, and m corresponds to the number of rows. Right, so if we look at this matrix and we go and calculate and we go and write down the reduced row echelon form. Now, what is the largest amount of non-zero rows that I can get? The largest amount of non-zero rows that I can get is in fact m. So the augmented matrix of this system has at most m leading variables. Okay, just don't forget that what I mean by when I talk about the augmented matrix, I mean the row echelon form of the augmented matrix. All right, so it's got m leading variables. So how many free variables does it have? So in worst case scenario, it will have at least the total number of variables minus your leading variables, which can be at very worst, at most m. So it will have at least n minus m free variables. Right, carrying on, as I said, remember we said previously it will have at least n minus m free variables. So therefore, it will have at least n minus 1 equals 1 free variables. Now listen, why, just quickly remember that we said that m is strictly less than n. And because n and m are positive non-zero integers, so remember that the biggest that m can become is, because it's strictly less than n, is the integer that comes right before n. The biggest that m can become is therefore n minus 1, right? So what this means is if it has n minus m free variables, then the smallest that n minus m can become is if m is the largest possible value it can take on, which in this case is at the very worst n minus 1. So therefore that just becomes 1. So n minus m is at least 1. Okay, so that means that your number of free variables is at least 1. As soon as you have a free variable, you have infinitely many solutions. Okay, so hence the system has infinitely many solutions. Right, so that concludes the proof of that theorem. Right, so let's just apply it to the following two examples. Determine which of the following homogeneous systems have non-trivial solutions by inspection. Okay, so here you've got a linear, homogeneous linear system. It's got 3 equations, 4 unknowns. So it's got more unknowns than equations. So basically that system has 4 unknowns and 3 equations. Right, so as 4 is bigger than 3, we have, by previous theorem, that the system has non-trivial solutions. Okay, right, let's look at the next one. If you write down the augmented matrix of this system, so it's going to be 3 minus 2, 0, and 6 minus 4, 0. Now, if you go and write it down in reduced row echelon form, you basically can do that by multiplying the first row with minus 2 and adding it to the second row. That's going to be 3 minus 2, 0, and that's going to be 0, 0, 0. Okay, so it's got a 0 row, and it's basically got a leading 1, or it's got a leading variable there. So basically what you can do to complete that reasoning is that the system so it has one leading variable, and so it has, by that first theorem we did previously, first one, theorem 1, it will have a total number of variables, which is 2 minus 1 leading variables. It will have 1 free variable. Okay, hence, so it has non-trivial solutions. It has non-trivial solutions.